Let's go ahead and look at an example. Let's solve example 3. Y double prime minus 3y prime equals to 8e to the 3x plus 4 sine x. We know that we can use the methods from this section because we have a linear differential equation with constant coefficients. Furthermore, the function g of x on the right-hand side is composed of those functions that are in our list of ones that we can annihilate with some linear differential operator. We'll begin these problems like we would do for the most part. We want to start by finding y sub c first. So let's start by finding the complementary solution by solving the homogeneous differential equation y double prime minus 3y prime equal to 0. The auxiliary equation would be m squared minus 3m equals to 0. This factors, set each factor equal to 0, and we get m equals to 0 and m equals to 3. Therefore, the complementary solution would be c1 plus c2 e to the 3x. Okay. So we have that part. Now what we're going to do is we want to find the particular solution y sub p. And it begins by finding an annihilator for g of x. So one of the things that we know, and this was a list that I linked to in D2L, is that if we look at 8e to the 3x, that function would be annihilated by, actually, hold on one second here. Do I have the right one? Yes, I'm sorry. So that function would be annihilated by the differential operator d minus 3. So d minus 3, this would annihilate 8e to the 3x. We also know that for sine x, this would be annihilated by the following. That would be annihilated by d squared plus 1. So d squared plus 1, that's going to annihilate for sine x. And now the third property of these ones that we were talking about, and by the way, this is example 4, not example 3. The property that we were talking about with differential annihilators is that if these two operators annihilate each of these ones individually, then it's the case that the product operator, d squared plus 1 times d minus 3, that will annihilate g of x. So that will annihilate 8e to the 3x plus 4 sine x. So what we're going to do is we're going to take and apply this differential operator to our linear differential equation. And in order to do that, first let's write the differential equation in operator format. So it's y double prime minus 3y prime. That can be represented as d squared minus 3d applied to y. This is equal to 8e to the 3x plus 4 sine x. And now let's go ahead and apply our new operator here. So we're going to apply to this d squared plus 1 times d minus 3. d squared plus 1 times d minus 3. We know what's going to happen on the right-hand side. This is going to annihilate the right-hand side, so it's going to be 0. And on the left-hand side, we have the following. It's d squared plus 1 times, that looks really horrible, sorry. We have d squared plus 1 times d minus 3. And now this differential operator we know factors as pulling out the common factor of d as d minus 3 times d. So we can kind of write it in exponential notation because we have 2 powers of d minus 3 squared times d applied to y. And now this is a homogeneous differential equation. We can set up the auxiliary equation. It would be m squared plus 1 times m minus 3 squared times m equal to 0. Set each factor equal to 0 individually. And here's what we get. This one would give us plus or minus I. This one would give us m equals to 3, which should be of order 2. And then we also have m equals to 0. So the solution is going to look like this. We're going to have y equals, let's handle the easy parts first. We have the 0. That's going to be c1. Plus now we have 3 of order 2. So that's going to be like a c2 e to the 3x. But then we also get a c3 x e to the 3x. And then this is a complex solution. Think of it as like alpha plus or minus beta I, where alpha is 0. So that's going to give us a c4 cosine of x plus c5 sine of x. And if we look carefully, there's a little bit of overlap between y sub p, the y value we have now, and our complementary solution. In particular, a constant, and a constant times e to the 3x is already included in that portion of it. Therefore, we believe that the particular form y sub p of the solution is going to include these terms here. And again, instead of calling them c3, c4, and c5, just because it's going to be a little bit easier to work with them, I'll call it ax e to the 3x plus b cosine x plus c sine x. So let's take the derivatives of y sub p, plug it into the differential equation, and see if we can solve for those undetermined coefficients. So y sub p, we said a moment ago, it's ax e to the 3x plus b cosine x plus c sine x. Y prime, if you use a product rule for the first piece, it's going to be a e to the 3x plus 3ax e to the 3x minus b sine x plus c cosine x. That would be our first derivative. Let's go ahead and take the second derivative. We're going to get 3a e to the 3x plus, using a product rule here, 3a e to the 3x plus 9ax e to the 3x minus b cosine x minus c sine x. We're now going to plug it into the differential equation. So it's y double prime. So I'll recopy y double prime. We have 3a. Actually, I can combine some like terms, by the way. These will combine. So we're going to have a 6a e to the 3x plus 9a x e to the 3x minus b cosine x minus c sine x. When I write it down, let's already go ahead and multiply y prime by negative 3. Multiplying this derivative by negative 3, we're going to get a negative 3a e to the 3x minus 9a x e to the 3x. That'll become a plus 3b sine x minus 3 c cosine x. And this is supposed to be equal to 8e to the 3x plus 4 sine x. We're now going to combine like terms on the left-hand side. One of the things I just kind of noticed immediately is that the positive 9ax e to the 3x and the negative 9ax e to the 3x, those two will cancel. We have two like terms here. 6 minus 3 will give us 3a e to the 3x. I'm now going to write out the coefficient of the cosine term. These are my two cosine terms right here. That's a negative b with a minus 3c. That's with the cosine x. And then our sine terms would be these two right here. That's going to have a coefficient of 3b minus c sine of x. And this is equal to 8 e to the x plus 4 sine x. We can now go ahead and equate coefficients. 3a will be equal to 8. There is no cosine term on this left-hand side, so this coefficient would be 0. So negative b minus 3c will be equal to 0. And the sine coefficients have to match up, meaning that 3b minus c will be equal to 4. The first one easily can be solved for a divided by 3, and we find that a is equal to 8/3. To solve for b and c, we can solve the subsystem, two equations and two unknowns. And the elimination method works pretty nice here. We can go ahead and, let's say, multiply the first equation by 3. That would give us a negative 3b minus 9c. 0 times 3 is 0. And then we have 3b minus c equal to 0. Add the two equations together. The left sides added together will produce a negative 10c. 0 plus 0 is, oops, excuse me, dropped a 4 here, it should be a 4. 0 plus 4 is 4. Divide both sides by negative 10. So c is negative 4/10, which would be negative 2/5. We can plug that now in to solve for c. In particular, if I come over here, if I add b to both sides, then I find that b is simply going to be negative 3 times c. So negative 3 times negative 2/5 should give us positive 6/5. So a is 8/3, b is 6/5, and c is negative 2/5. And that gives us our general solution. So remember, the general solution is the complementary solution plus a particular solution. We said that the complementary part was the stuff that's in yellow. That was c1 plus c2e to the 3x. Plus, we were calling it a previously, the coefficient of the x e to the 3x term. That was 8/3 x e to the 3x. The b was the coefficient of the cosine term. So that's going to be plus 6/5 cosine of x. And then the c was the coefficient of the sine term. So that's negative 2/5 sine of x. And so that gives us our general solution to this differential equation.